SN1987A was a supernova in the outskirts of the Tarantula Nebula in the Large Magellanic Cloud. It occurred approximately 51.4 kiloparsecs from Earth, approximately 168,000 light-years, close enough that it was visible to the naked eye. It could be seen from the Southern Hemisphere. It was the closest observed supernova since SN1604, which occurred in the Milky Way itself. The light from the new supernova reached Earth on February 23, 1987. As it was the first supernova discovered in 1987, it was labeled 1987A. Its brightness peaked in May with an apparent magnitude of about 3 and slowly declined in the following months. It was the first opportunity for modern astronomers to study the development of a supernova in detail, and observations have provided much insight into core collapse supernovae of special importance. SN1987A provided the first chance to confirm by direct observation the radioactive source of the energy for visible light emissions by detection of predicted gamma-ray line radiation from two of its abundant radioactive nuclei, 56Co and 57Co. This proved the radioactive nature of the long-duration post-explosion glow of supernovae. Discovery. SN1987A was discovered by Ian Shelton and Oscar Duhalde at the Las Campanas Observatory in Chile on February 24, 1987, and within the same 24 hours independently by Albert Jones in New Zealand. On March 4–12, 1987, it was observed from space by Astron, the largest ultraviolet space telescope of the time. Progenitor. 4 days after the event was recorded, the progenitor star was tentatively identified as Sandlich-69°202, a blue supergiant. After the supernova faded, the identification was definitely confirmed by Sandlich-69°202 having disappeared. This was an unexpected identification, because at the time a blue supergiant was not considered a possibility for a supernova event in existing models of high-mass stellar evolution. Many models of the progenitor have attributed the color to its chemical composition, particularly the low levels of heavy elements, among other factors. There has been some speculation that the star may have merged with a companion star prior to the supernova. However, it is now widely understood that blue supergiants are natural progenitors of supernovae, although there is still speculation that the evolution of such stars requires mass loss involving a binary companion. It is of note that the supernova of the blue giant Sandlich-69°202 was about 1/10 as luminous as the average observed Type II supernova, which is associated with the denser makeup of the star. Because blue supergiant supernovae are not as bright as those generated by red supergiants, we cannot see them in as large a volume. We would thus not expect to see as many of them, and so they might not be as rare or unusual as previously thought. Neutrino emissions. Approximately 2 to 3 hours before the visible light from SN1987A reached Earth, a burst of neutrinos was observed at 3 separate neutrino observatories. This is likely due to neutrino emission, which occurs simultaneously with core collapse but preceding the emission of visible light. Transmission of visible light is a slower process that occurs only after the shock wave reaches the stellar surface. At 7:35 Cameo-Can2 detected 11 antineutrinos, IMB 8 antineutrinos, and Baksan 5 antineutrinos, in a burst lasting less than 13 seconds. Approximately 3 hours earlier, the Mont Blanc liquid scintillator detected a 5 neutrino burst. but this is generally not believed to be associated with SN1987A. Although the actual neutrino count was only 24, it was a significant rise from the previously observed background level. This was the first time neutrinos known to be emitted from a supernova had been observed directly, which marked the beginning of neutrino astronomy. The observations were consistent with theoretical supernova models in which 99% of the energy of the collapse is radiated away in the form of neutrinos. The observations are also consistent with the model's estimates of a total neutrino count of 1058 with a total energy of 1046 joules. The neutrino measurements allowed upper bounds on neutrino mass and charge, as well as the number of flavors of neutrinos and other properties. For example, the data show that within 5% confidence the rest mass of the electron neutrino is at most 16 electron volts, C2, 1/30,000th the mass of an electron. The data suggest that the total number of neutrino flavors is at most 8, but other observations and experiments give tighter estimates. Many of these results have since been confirmed or tightened by other neutrino experiments, such as more careful analysis of solar neutrinos and atmospheric neutrinos, as well as experiments with artificial neutrino sources. Missing neutron star. SN1987A appears to be a core-collapsed supernova, which should result in a neutron star given the size of the original star. The neutrino data indicate that a compact object did form at the star's core. However, since the supernova first became visible, astronomers have been searching for the collapsed core but have not detected it. The Hubble Space Telescope has taken images of the supernova regularly since August 1990, but, so far, the images have shown no evidence of a neutron star. A number of possibilities for the missing neutron star are being considered, although none are clearly favored. The first is that the neutron star is enshrouded in dense dust clouds so that it cannot be seen. Another is that a pulsar was formed but with either an unusually large or small magnetic field. It is also possible that larger amounts of material fell back on the neutron star so that it further collapsed into a black hole. Neutron stars and black holes often give off light when material falls onto them. If there is a compact object in the supernova remnant, but no material to fall onto it, it would be very dim and could therefore avoid detection. Other scenarios have also been considered, such as if the collapsed core became a quark star. Light curve. Much of the light curve, or graph of luminosity, is a function of time. After the explosion of a Type II supernova such as SN1987A is provided its energy by radioactive decay. Although the luminous emission consists of optical photons, it is the radioactive power absorbed that keeps the remnant hot enough to radiate light. Without radioactive heat it would quickly dim. The radioactive decay of 56Ni through its daughters 56Co to 56Fe produces gamma-ray photons that are absorbed and dominate the heating, and thus the luminosity of the ejector at intermediate times to late times. Energy for the peak of the light curve of SN1987A was provided by the decay of 56Ni to 56Co, while energy for the later light curve in particular fit very closely with the 77.3-day half-life of 56Co decaying to 56Fe. Later measurements by space gamma-ray telescopes of the small fraction of the 56Co and 57Co gamma rays that escaped the SN1987A remnant without absorption confirmed earlier predictions that those two radioactive nuclei were the power source. Because the 56Co in SN1987A has today completely decayed, it no longer supports the luminosity of the SN1987A ejector, that is currently powered by the radioactive decay of 4040 with a half-life of about 60 years. X-ray lines from 4040 observed by the Integral Space X-ray Telescope showed that the total mass of radioactive 4040 synthesized during the explosion was 3.1 plus or minus 0.8 times 10⁻⁴ m. Observations of the radioactive power from the decays in the 1987A light curve have measured accurate total masses of the 56 Ni, 57 Ni, and 4040 created in the explosion, which agree with the masses measured by gamma-ray line space telescopes and provides nucleosynthesis constraints on the computed supernova model. Interaction with circumstellar material. The three bright rings around SN1987A are material from the stellar wind of the progenitor. These rings were ionized by the ultraviolet flash from the supernova explosion and consequently began emitting in various emission lines. These rings did not turn on until several months after the supernova. The turn-on process can be very accurately studied through spectroscopy. The rings are large enough that their angular size can be measured accurately. The inner ring is 0.808 arcseconds in radius. Using the distance light must have traveled to light up the inner ring as the base of a right-angled triangle, and the angular size is seen from the Earth for the local angle. One can use basic trigonometry to calculate the distance to SN1987A, which is about 168,000 light-years. The material from the explosion is catching up with the material expelled during both its red and blue supergiant phases and heating it, so we observe ring structures about the star. Around 2001, the expanding supernova ejector collided with the inner ring. This caused its heating and the generation of X-rays. The X-ray flux from the ring increased by a factor of 3 between 2001 and 2009. A part of the X-ray radiation, which is absorbed by the dense ejector close to the center, is responsible for a comparable increase in the optical flux from the supernova remnant in 2001 to 2009. This increase of the brightness of the remnant reversed the trend observed before 2001, when the optical flux was decreasing due to the decaying of 4040 isotope. A study reported in June 2015, using images from the Hubble Space Telescope and the Very Large Telescope taken between 1994 and 2014, shows that the emissions from the clumps of matter making up the rings are fading as the clumps are destroyed by the shockwave. It is predicted the ring will fade away between 2020 and 2030. As the shock wave passes the circumstellar ring, it will trace the history of mass loss of the supernova's progenitor and provide useful information for discriminating among various models for the progenitor of SN1987A.